name's Bob O'Barra. I'm one of the assistant directors in the scientific computing team here at Kitware. Joining me is Dr. David Thompson, who is also a principal developer here in the scientific team. We are also both chief architects of the Computational Model Builder project, which we're going to be talking about aspects of during this webinar. Before we get started, I'm just going to give a brief overview of what we're going to talk about. I'm going to give a little introduction to Kitware, as well as an introduction into WaveTank workflows. David will then do a live demonstration. And then we'll go back and we'll talk about some of the workflow challenges, how CMB's task approach can address some of those, as well as a summary of benefits and next steps. In terms of Kitware itself, we're a leader in science, in software and AI research and development, partnering with government agencies, academia, and industrial leaders in order to tackle complex problems in computer vision, medical, sorry, hold on for one sec, medical imaging, scientific computing, and high-performance software systems. Our mission is to produce cutting-edge open-source tools that will accelerate discovery and empower innovation, whether or not it's in the lab, clinic, or in the field. We have over 200 engineers, researchers, and developers spread across 6 different offices across the US and in Europe, including New York, North Carolina, New Mexico, Virginia, Minnesota, and Lyon, France. This distributed collaborative culture fuels our ability to develop impactful solutions on a global scale. At the heart of our company is a deep commitment to open source itself. We believe in developing sustainable platforms that bring communities together, platforms like TRAM, 3D Slicer, ParaView, and today's spotlight, Computational Model Builder. These tools just don't solve problems, they encourage collaboration, accelerate progress, and form foundations for the next level of innovation. Okay. With that said, I'd like to get started in terms of introducing WaveTanks. Some of you may be familiar with these. In the past, these were physical systems that generated real-life waves, so you could do certain forms of simulation analysis. These models typically had physical actuators and instrumentations, which can make them somewhat expensive to run. This is an example of a WaveTank at a university, as well as this is one at the Army Corps of Engineers lab for actually modeling very complex waves. Besides the fact that they can be expensive and they take up physical space, other reasons to prefer simulation is that there are certain aspects of WaveTanks that are very difficult to scale. If I'm reducing something from an ocean size to something that's going to be in a limited space, some things just don't scale properly. Viscous forces is one of the major ones. You know, they can become much more significant at smaller scale. So if I reduce the problem, I'm going to introduce some inaccuracies inside of my simulation, as well as things like material properties. They may not scale properly if I'm going to 1/100th or 50th of scale, as well as monitoring things like wind-wave interactions. In addition, you have to deal with complex problem of wave generation and absorption. Because you're dealing with a finite space in the physical system, you have to worry about reflections and so forth that are set up in the system. How do you get rid of them? Because in the real world, you wouldn't have those. Physical simulations allow us to have sort of unbounded system. Modern WaveTanks are still, they're largely computational. And setting these up can be challenging. For example, if you have to have your geometry properly configured, you have to have it, meshing becomes sort of critical. If you don't have your meshing sized properly, you might miss important features or timescale issues of interest. And anyone who's run numerical simulation as well as things that involve mesh generation, there is a lot of parameters that typically have to be set up in order to appropriately model the scenario that you want to deal with. With that said, I'm going to switch over to David, who is going to walk you through the Computational Model Builder WaveTank workflow that we've set up. So, David?
Sure. Hi, everyone. So this is our virtual WaveTank here in Model Builder. It's a custom application built on top of CMB. And I'm starting off with just the bare application. I have a toolbar button here that lets me create a project. And you'll notice when I click down at the bottom left, these two worklets appeared. So you can set up your projects with Model Builder such that you have kind of a default workflow that's maybe a fixed set of things that users need to perform. But for this one, they wanted to be able to go through different workflows to compare what-if scenarios and so on. And so at the top level, you just drag a worklet over, and you'll see this one this is a task now, and this task has a folder icon that indicates it has children. So all of these subtasks are required to perform, you're required to perform them to do a single study of a 3D WaveTank. And so you can see there are a bunch of tasks. These are things that users have to perform in order to complete the study. They're not necessarily related to computational action. They can also be just information gathering, that kind of thing. You'll also notice that to the left of each task title, there's a little color blob there. So these indicate, for instance, that this task is incomplete because it's yellow. This snappy mesh task is red, that indicates it's unavailable. And things like inertial properties, since there are defaults here, default inertial properties, it's completable, but obviously since we haven't loaded a device in, it's not correct yet. So you can start anywhere where a task is either incomplete or completable. And so we could start at background mesh here. And you'll notice when I clicked on the study, it put some objects into view. So this is kind of the default WaveTank. You can see that if I click on one of these little handles here, I can change the dimensions interactively, or I can just go into the text box here and edit the dimensions to be nice round numbers. But these let you perform, both interactive and value-based editing of the region that's going to be the simulation domain. You can see I have these paddings here. If I had loaded a device in, then I could add some padding or margins around the device to make the WaveTank the size that I wanted, either in terms of an absolute length or a scale factor. And once I'm done, then I can actually run OpenFOAM to create the background mesh. This shows me what OpenFOAM did, and I can go down to the bottom here again and load the mesh that it created in. That draws it. I can also turn on surface with edges and just kind of get a feel for how finely discretized the domain is. Once I like the settings, there's nothing stopping me from changing the number of cells or the size of the domain. Once I've finished rerunning, then I can click complete, and now this task here has been marked complete, both through the checkbox and the color here to the left of the title. So normally there might be a linear order here. I might come over and work on the overset mesh. You notice I can't work on snappy yet, and there's these two brown lines here. Those indicate things that the author of the workflow inserted, saying you're not allowed to work on snappy hex meshing until you have an overset mesh and a device geometry loaded. So I can go work on device geometry. It's got some nice instructions up here. I happen to know that I have a motorboat that I'm interested in simulating, and I also know that its units are in millimeters, not meters. As a workflow author, you can choose the units that you want, length and other units that you want the quantities to be in across the simulation, and users are allowed to enter things in whatever units they want, and it will do conversions for you. So when I load this in, it's going to scale this down by a factor of 1,000. When I click the import button, you can see the boat that I have. I also have controls up here to turn on and off the visibility of the wave tank itself. If I zoom in, you'll see there's a little dot here. It's kind of hard to see, but my cursor changes when I'm over it. It's asking me to identify a model point inside the object, and so this one is not clearly inside the object. So what I'm going to do is press the P key over here, and that snaps it to a point on the model. And because I know the model is symmetric about the y-axis here, I can just come in and change the y-coordinate to 0 there. I also have a little control to change the opacity of this, and so as I zoom in, you can see that the model point is completely contained inside the mesh here. So that will be important later when we actually get to meshing. I can also do things like rotate the model and scale it, translate it, whatever I need to do to get it set up right. I actually have this model placed just a little bit above the water surface, which is shown in blue here inside the simulation domain. I am doing that so that we'll do a drop test and drop it in and let it settle down to the height, the draft that it normally would pull. So once you're happy with this task, we can mark it complete. I can go choose an overset mesh. It's not being shown right now because it's possible to run without one. I'm going to pad it to the size of the object, the device I just imported. And when I click box here to enable the overset mesh, you can see it's placed just a meter out from the bounds of the ship, the motorboat. Now, this task won't be complete until I actually have an overset mesh, so I'm going to go ahead and run and just accept the default resolution of the mesh. I could continue down here and load the data and inspect it. It would be very much like the background mesh that we just inspected. So again, once you're happy, yes.
We have a question. Somebody had asked, why are some of the values yellow versus some of the values being white?
That's a great question. So if I go edit a value like this, it becomes non-default, and so it turns white. If you can see there's a tooltip there as well, so it tells you kind of the range that you're allowed to enter. And then if I right-click, I can reset it to the default, and it will turn yellow again. If I enter an invalid value, like no value at all, it actually turns red.
Thank you.
So once I've completed that task, it takes me back to the workflow diagram, and we could work on generating a snappy hex mesh of the device. This is basically takes the overset mesh and carves out the shape of the device, the motorboat, from the hex mesh that's the overset mesh, and produces a hex mesh output with some voids in it. That takes a while to run, so what I'm going to do is switch to another instance where, look, I've just completed a snappy hex mesh of this. it's possible for me to go in and inspect the result in the mesh if I want. I'm going to actually do that here, and I'm going to enter pair view mode. So CMB comes, it's built on top of pair view, and now you can see, for instance, the pipeline browser is here. I'm going to turn off the geometry so that I can see just the product of the Snappy Hex Mesh run, and I'm going to make sure auto apply is off and run a clip filter on this so I can take a look at the inside of the mesh. I also am going to come over to the pair view properties panel, which if you've run pair view you might be familiar with, and switch the plane here. And then I'm going to make this crinkle clip, and when I apply it, you'll see the mesh that it produced with the voids inside, where there's solid material for the boat. So once I'm done with that, and I'm happy with the quality of the mesh, I can come back to the Snappy Hex Mesh stage of the workflow diagram, and because I've run the mesher, I can mark it complete, and from there on we can do more stuff. So you'll notice there's this red box here that wasn't in the last one. That's actually a refinement region. So you can add refinement regions to the background mesh as you like. I can't edit these because it's been marked completed, so it will stop me from adding new attributes and so on. But you can go through and add as many of these as you want. So once you have all of the background and the device overset mesh created, you can merge the meshes. This is a fast operation. It doesn't even really need to be a task, except that sometimes people like to inspect the mesh here and just ensure that it's complete and that you merge properly. So now there's some other stages here. Setting up constants, for instance, if you want to simulate something in a fluid other than water or air, you can add that, and I don't care to change any of that. You can also, I'm going to go back here for a moment to Snappy Mesh and hide the grid there so that when I come, so boundary conditions lets you change things like the water surface level. So I can move that around as I like. I don't have any other things to edit there, but wave properties are available there. We also let you add tethers and things like that. You can also constrain the motion of the object. So for 2D simulations, for instance, you might prevent any translation in the Y direction, side to side. And so if I create a new tether, for instance, I can attach one end to the ship. Oh, I can rename the tether first. And once the focus is actually in the 3D view here, if I click the one key, it will snap a point onto the ship. You are also free to edit those points and down below here. And I can have control on the visibility of these other related regions. So for instance, I could snap the other end to the simulation boundary, and that lets me add tethers as I like. Now I could go up here and try and click complete, but it won't work because I haven't finished filling this attribute out. Talking about the tether, I haven't specified a free length. Now you can see down below there's a length of the tether as it currently is, which is 5 meters. So it's 5.4 meters. So I could add in, say, a 5 meter free length, and it shows me the initial tension in the cable given the spring constant. So you can add as many of these tethers as you like, and other things. Once you're happy, you can mark this task complete. And finally, we get to running OpenFOAM, and you can choose to run it in parallel or in just on your laptop without running MPI or anything. If you run it in parallel, you can choose the scheme for the decomposition of the mesh, and you can choose parameters like start time and end time and so on. And I'm not going to click run here because a meaningful simulation would take a while. But unless I've forgotten something, we'll skip that, and we'll go back to the slides, and you can actually see the results of the simulation post-process. Do you have anything to say?
Yep. Before we continue, there's a couple questions I'd like to address. One person had asked, tasks sometimes form a logical workflow, pre-processing, meshing, solving, post-processing. Can you define default graph layouts such as left to right display instead of having a full graph in terms of a workflow?
You certainly can. So this diagram editor, I haven't showed much of it, but you can organize the tasks however you like. So if I wanted these two tasks to be vertically aligned, for instance, I can do things like this where you move them around. There's also an auto layout feature in the task editing mode that will auto group things using GraphViz to lay the nodes out based on their arcs. So there's some control over that the workflow author has, and then users who are just working through the workflow can move things around as they like.
Yeah, and also to just contribute off of that, there's also other ways of displaying the work. For example, what I think the person is referring to is sometimes like if you look at the wind tunnel example that we did several months ago, that was an implied workflow where we gave a tab, and in that tab view, you went from left to right, and you did those steps in linear order. That's another way of presenting the task. So it really depends on terms of the workflow that you want to deal with, and if you want to give the user flexibility in terms of, they could either do A or B. For example, in the workflow that David's showing right now, theoretically speaking, you could actually, in this same workflow, simulate just the wave tank itself, no object, no nothing. And you would just go all the way towards the end and set up that problem. So it's just that this workflow was given a fair amount of flexibility based off of the requirements off on that. So I hope that basically that answers that question. Another one was were the tasks we're showing developed for the wave tank application, or are they natively available in CMB? The task system is core to CMB. Where it's the monitoring of state, connectivity, and so forth. How those operational tasks behave, the tasks that actually perform operations, as well as the type of information that's being modeled. All of that capability is inside CMB and its underlying library, SMPK. What is custom here is the actual, what is the function that I'm actually going to run? What is the operation I'm going to run? What is the information I'm going to describe? What is the boundary conditions and material properties that need to be specified by the problem, by the workflow in particular? That is the stuff that gets authored from the user, from the designer. But all the rest of the underpinnings is all available within CMB itself. David, you wanted to bring up something?
I was just going to provide a little bit. So we do have a slide later with some of the JSON examples here, but the idea is that tasks have agents that kind of monitor the status or provide some feedback to users as they complete things. And so we have a set of pre-configured agents that will validate portions of the workflow here. So I'm saying you need to provide this information about castellation and snapping as part of Snappy Hex Mesh. So I didn't have to write something new just for the wave tank to use that. I just had to tell it, these are the attributes that I want you to validate as part of this task. And similarly, it has another agent here that forwards information from the input ports to the output ports, so that any task downstream of it can use not only the attributes that the user filled out on snapping, but also have access to the geometric model of the motorboat. So you build the tasks up out of these blocks.
Another question was, can we embed other renderers other than the render view in CMB, like the Python visualization view, which is available in ParaView?
Yep, it's pair view, so you can put whatever views in that you like. Now, unless you go into pair view mode, you might not find anything interesting, but it's certainly possible to have other views of the data.
Okay. All right, and one last question before we move on was, how does CMB handle cluster submission, taking into account that each cluster will have its own specificity? We have done workflows that actually involve HPC. So for example, we did work with NERSC and high energy physics, and we actually integrated into the job submission environment. So for example, when a task was going to say, hey, run the simulation, it would bundle everything up, submit it over to the queuing system, and then have a monitoring system that would go ahead and check in on it. So the guts on that one is you can do it, and we have done it. It's just that basically, as you know, each clustering and submission system tends to have its own personality. So in some ways, you wind up creating a library of, hey, this is a task that can submit to system A. This is one that can submit to system B. All right, I hope that has answered folks' questions for right now. All right, switching over. I'm going to switch over to my screen. Back again. All righty. Oops, sorry. Give that control. So, David, you want to make any comments?
I'll just note real quick. This is the simulation I configured. It's showing the alpha water thing being iso-volumed, so that's why only the water surface is showing, and the coloring on the water is the pressure minus rho GH, so that you can see things besides just the pressure increasing with the depth. And it drops the boat down, and the boat eventually settles, but because of the waves coming in at that top right boundary, you can see that it starts moving forward. The boat starts moving forward a little bit as the simulation progresses. But there, I could have specified no waves, and things would work out just fine.
Alrighty. Okay. Taking a step back and looking at some of the challenges with this workflow, as well as workflows in general. And this goes back to one of the questions in terms of somebody had asked, can you simplify things so the workflow only goes from left to right? We actually did that. I call that an implicit workflow that we have modeled for the wind tunnel, because technically speaking, yes, the user went from left to right and it walked them through all the stages. However, if the user went backward and made a modification in a tab, they had to remember that they needed to, oh, I have to go back and do those other steps and repeat those. In this, that can be a little bit complicated, because that means the user is walking away with the workflow state in their brain as opposed to in the workflow itself, which is where it probably belongs. Also, as you can see in David's, the general wave tank problem, you can get lost in the details. It's very easy to go, well, here are all the pieces you need to deal with. Where do you want to start? Where can I start? you need to be able to give the user options in terms of here are entry points that you can get work done, here are things that you can't do, and there's a reason for why you can't do them. Is the workflow up to date? Is another thing. Well, if I made a change upstream, what parts of the workflow downstream now need to be recalculated or redone? Which goes back to the one I just skipped, which was knowing what's left to be done. In other words, am I finished? Did I do everything appropriately? In addition to all that, tracking all the related resources. David didn't show it, but there's a lot of files that get generated between running the meshers and running OpenFOAM itself. David, give a ballpark in terms of how many files the wave tank took?
It's about 20 or 30. Yeah.
Okay. And knowing basically how to track all those files, what files have to be deleted, removed when you're removing workflows, studies and so forth can be challenging. Providing flexibility and choices. As before, the reason why this workflow is a little bit more complicated is that it allowed the user not just a fixed set of things. I'm only going to be dealing with a ship in a 3D wave tank. You could do a 2D problem. You could do a 2D problem with no object in it. And the idea is that basically as you move forward, you want to have flexibility to go, okay, fine, I did the wave tank, I simulated no object waves. I want to take that same piece and now I'll put objects in it. So you have to give flexibility. There is benefit of the other ones too, don't get me wrong. I tend to call those micro workflows where basically I want to reduce a lot of degrees of freedom so that the user is more easily guided, and we can support those just as easily. And then collaboration. A lot of cases, I may know meshing very well, and somebody else may know the physics of the problem. Can we both work on the same workflow? Can they do their part? Then they go, hey, give me a mesh that's required. Great, it's done. Okay, you can continue, and it's all stored within one system. Let's take a little bit deeper dive in terms of what we, SMTK, which is the Simulation Modeling Toolkit library, which is part of CMB. For those of you that know ParaView, SMTK is to CMB as VDK is to ParaView. Well, most of the work that we do, almost all the functionalities inside SMTK, leaving CMB to be a very small branded version of ParaView. Tasks allow the user to decompose the workflow into conceptually clear pieces. It can focus on information modeling, as David showed, specifying boundary conditions, or it can focus on operation execution. David sort of hinted, these pieces are managed underneath the covers by what we call agents. So agent, a task can have agents, guys that are actually worried about what has to be done within the task, and they come together and set how the task state is currently reflective. Operation-focused tasks can be defined as a run once. For example, for those of you who are meshing, you might have a task that says, create me a surface mesh. You do that once. Other tasks might be something that you may run multiple times. The one that comes to mind, since I do know meshing a little bit, is mesh smoothing. So you can set tasks to do that. You can also set operation-focused tasks to auto-complete themselves, to mark themselves incomplete if any of their inputs have changed. You can also mark them to auto-complete if they successfully run. Task state, David did a good job in terms of describing this. I'm just going to reiterate, there are typically 5 states to a task. The completed, I'm done, user has marked it as finished. Completable is the case where the designer has said, I can tell you what the minimum requirements are, but it might be up to the user to determine whether or not they are done. For example, David, some workflows, you may have a set of good defaults. Well, they did provide specification of, say, a boundary condition or a material property, but the user is free to change those. So it's completable, but the user has decided it's not done yet. Incomplete, that's pretty straightforward. You're missing information. You haven't specified everything else. Unavailable, my dependencies have not been finished. You can't move forward to me until you get that other work done. The irrelevant one is very interesting. Irrelevant means that the task is no longer applicable to the workflow, and you might be asking why. That one shows up more in multi-physics than anywhere else. Say you've got a workflow that can do CFD and structural mechanics and thermal and heat transfer, and at the very beginning of the workflow, you could say, right now, I'm just going to look at the CFD, computational fluid dynamics part of the problem. Well, at that point, anything that relates to the other two physics may suddenly go, okay, fine, I'm no longer applicable. I am going to hide myself. The system would filter out the workflow and say, okay, this is what you have to work on. If later on you change it, those tasks come back, and the user can then work on them in the future. Connectivity, as David talked about, there's two forms of connectivity that we deal with. One is dealing with data connectivity or data dependency, where each task can have inputs and outputs, multiple inputs and output ports, very similar to what ParaView and BTK support in their filters, and it allows things to be having a task accept and transmit data about the work that the user needs to perform. Tasks can also have conceptual dependencies. That's what's forcing order. So if you wanted to do the example of a linear workflow, you would just have task A depend on task B, depend on task C in a linear line, and then they have to do C, B, A in that order. Task ports also allow the ability to exchange information. Remember, David said that a task can have children. Well, being able to have a child send data to the parent's output port, for example, allows you to basically have communication between internal pieces that are sort of obfuscated to the rest of that upper workflow, and have things work sort of nice and smoothly. Same thing's true for input. You can have data coming into the parent task input port, and now a child may say, oh, I want to grab that data coming into that task. I'm going to work on that piece. Interactivity. Each task can determine how CMB's panels are configured when active. So as David showed, he selected a task. Suddenly the 3D screen changed. Also, the 2D, the attribute editing panels, for example, changed to reflect what the task, what the agents in that task want the user to do. This can be really useful. For example, I might have the boat geometry coming in, but then if I have to assign boundary conditions to parts of the boat, when I get into that task, I may now color the model based on what boundary conditions have been assigned. So the user didn't have to worry about doing it, and the developer, the task designer, did it once. He programmed it into the workflow. Now it's there. No one has to necessarily worry about maintaining that. Finally, the developer can add and change the new UI elements into the system. So the task system and task management is part of the core of SMTK, but the UI piece is actually in another library. So if you wanted to, and I did this actually in the graphs, I was able to swap out different style of nodes in there because I wanted to have a different style. I could do that without disrupting anything. I could just add those in and then have a workflow refer to that functionality. So that gives the developers a lot of flexibility. Okay. In terms of reusing tasks, one of the things that probably should point out, and David stopped me, disagree, is that the fact that in that OpenFOAM wave tank workflow, there's a bunch of tasks in there, for example, controlling snappy, snappy hex mesh, merging mesh, and so forth. Those tasks, in theory, are reusable. And in fact, if you wanted to have, you're a designer that wanted to have, I don't know how these pieces are going to be connected. I'm going to do that on the fly. You can create what we call worklets, where they're basically sub workflows. They're connected tasks, or in some cases a single task, that can be dropped in. Whether that's at the top level of a workflow or you're inside a task, say, I'm going to generate a volume mesh. Well, you open that up, maybe I'll have a snappy hex mesh child and a merge mesh child and so forth in there. It allows you to be able to reuse things. Workflows themselves are connected, so they're already been pre-wired in those cases. And as before, a designer can indicate whether or not a workflow can be added to the top level, or, hey, if this workflow, if this workflow, worklet, or active task has these characteristics, then it can accept these type of worklets to be dropped into them. Task authoring, we did, because we didn't want to have a lot of coding in there, we use JSON. So you can do things such as, specify the requirements, the operations the user want to run. And here is a case where, for example, somebody asks, can we use operations in a C++ library? Or, for example, Python library that has been linked in using a plugin. This is where you basically connect things up. It doesn't have to be a OS, I'm going to launch an external process. We did that for OpenFOAM because that was the easiest thing to do where OpenFOAM was concerned. But if you have things that are more library driven, you can easily integrate those into your tasks. Okay.
Bob, we do have a question here.
Mm-hmm.
In the CMB example, I heard once a task is completed, we can't change the input parameters. Does that go to tasks defined in the GUI built over SMTK as well? To give more context, the block mesh was finished and marked in green. Can I redefine the grid size? I'll go ahead and answer that one. You can. You just have to mark the task incomplete before you can go in and edit any parameters. And when you do mark it incomplete, that lets the system know, oh, that means that the operation needs to be run again. So it won't let you complete it until you've edited things and rerun the block mesh. Does that make sense?
Yeah, there's no such thing as basically freezing a task. However, we do want to make sure that we know that the user intended to make a change on something, so that, as before, downstream stuff knows that, oh, I now need to recalculate, I might have to reassess myself. Any other questions? Okay, moving on. I just want to make a quick note on the CMB application itself. It's based on ParaView. All ParaView's functionality is fully available. By default, it's not fully exposed. Hence, when David had hinted at when he said, I'm now going to enter ParaView mode, which is we provided a mechanism that basically says, look, I do want to see all ParaView right now, and it exposes everything, including the ability to load additional data into the system that's not CMB specific. The look and feel itself, like ParaView to some extent, is controlled by plugins, but unlike ParaView, it also is controlled by the workflow. In other words, yes, you can. It does add a little complexity when you're doing your workflow if you want to take a lot more control over ParaView, but it also makes it so that you don't have to brand ParaView for yourself. That basically there's a fair amount of flexibility within both the workflow, which I refer to as the top level, as well as the active task. Hey, the active task is here. This is now wants to change what's available to the user, both in the ParaView UI as well as in CMB's UI. Okay. This was a sort of a summary slide I put in here in terms of CMB benefits. One of the main things of being able to do this is to facilitate knowledge coming from the simulation workflow expert and designer to the users that are going to be applying that workflow. it puts the expert at the beginning of the process, where in conventional systems, traditional systems, sometimes it was like the expert has to come in and, you know, bits and pieces with the workflow to make sure things have been properly set up. The focus is on end user instead of the solver, instead of solver and tools. What I mean by that is, and David, I'm going to point on one of the things that David showed, in that, remember the padding example when he was padding around, you know, creating padding around the object? That's not part of OpenFOAM. Because we're abstracting out on top of OpenFOAM, we're not slave to it. So we can actually change the tone to be better matching to the end user as opposed to matching to the solver, which is typically makes the workflow a lot more intuitive to the end user and a lot more understandable. It removes a lot of need for glue code, because in some ways CMB is the glue code. It actually allows you to connect a bunch of different types of tools. For example, you saw the use of Snappy Hex Mesh as well as OpenFOAM. In other workflows, we've used Gmesh, we've integrated OpenCascade, we've done a bunch of other, being able to put together a bunch of different tools all within one system. Semantic and syntax checking is available. The tasks themselves can do semantic checking. The information description mechanism, our information modeling system, can also do syntactical checking, making sure the user has put in values that are supported. As you saw, we have workflow task management inside CMB. It's a single customizable application framework, similar to ParaView, with little or no compilation necessary to specify simulation input. In other words, a lot of our stuff, operation-wise, if we're not calling an external routine, the easiest thing is to basically, you know, wrap the code up in Python and create Python-based operations, which are easily integrated inside the system. So once again, we do support both C++ and Python as major ways of extending the system. And also a permissive open source license. It is like ParaView BSD, so it can be used in both open source, viral open source, as well as closed source applications. In terms of moving forward, speaking respect to Kitware itself, you can get information on the source code for CMB. It's hosted by our GitLab repo. If you need more help, we also provide discourse. We can also provide support and training. There's up to several different ways of requesting that type of payment off on that. We can help you with software customization. For example, if there's a workflow that we can help put together an initial workflow. We can also help add new features that may be required for a specific workflow. And collaborative research. We are very open to being co-PIs or subcontractors on funding opportunities. Always feel free to reach out to us and to me, especially if it's connected with CMB. I want to also not take this time to do a special acknowledgement. This work was done with Sandia, with a great team there that we've been working with as part of the U.S. Department of Energy's Water Power Technology Office. And once again, a big shout out to that, because a lot of what you see in this task work came out of, a lot of those features came out of this work.
And there's a lot of additional features that we're working on with them to kind of expand the repertoire there. More boundary conditions and things like that.
Okay, and do we have any other questions?
I don't see anything else.
All right. Yeah, I once again want to thank everyone for attending. I hope you found this interesting. If you have any additional questions, there will be a survey sent out after the webinar is finished. So please fill that out. We really want to hear from you in terms of what you thought, things you like, things you like to, things that maybe follow-up information, follow-up questions, or follow-up webinar ideas off on that. And once again, thank you all very much for attending, and you all have a good rest of the day.